Lecture 11, which is about the control and operation of wind energy power hydrogen systems, and will be talked by Professor Jahangir. Over to you, Professor.
The microgrid that we discussed is not like any significant difference, like when you have only a hydrogen and green hydrogen system. So, it's quite similar. Only things, what is happening like here, that the green hydrogen system use output power from wind, either to produce hydrogen or again convert hydrogen to electricity. But other than that, there are not any like a significant difference. So, what I am going to do here, I am going to go like some discussion on the wind energy system, because we already have talked about hydrogen, and then I am going to show like one example that when you have got hydrogen wind system, how we can model it, and also the control technique that we discussed previously, how we can apply and check their performance. But in terms of like overall technique, there are not that much significant difference. So as you know that although we are talking about both solar and wind, but in many cases in many country, like wind power actually dominate over solar, and the reason is that from a single wind turbine, do you have any idea like what sort of output power we can get from like a big size wind turbine? Like 15-16 megawatt, like 16 megawatt wind turbine is currently available. And you see, if you want to get even like 10 megawatt output power from solar, how big or how many houses you need, right? You need plenty of space. So, that is one of the reason, like in any country where the space and location is a problem, then definitely wind farm, that could be a better choice. But having said that, for community microgrid, community don't like, in many cases many community don't like wind farm, because they say like it produces noise and so on for environmental reason, but that actually problem also has been addressed. Now, if you have like a new wind farm, their noise level even less than whatever pump we normally use for water or agriculture. So, noise actually is not any more issue. Another thing, many country like even in Australia, now they are planning for number of offshore wind farm. So, all the like space that we have like in the water, like sea and things like that. So, you put wind turbine over there, you are not using any like usable space. So, only thing you just need to build transmission line, which again as I mentioned that people going more like high voltage DC. So, that is the only things you need. So, in Australia, that they have already actually planned number of new offshore wind farm, and not only of Australia, like in Germany, Denmark, they are also having like number of new wind farm as well. So, again as I said, like if you have wind powered hydrogen microgrid, it would be that initially we are generating electricity from wind, and then you convert either excess energy or even like whatever, it could be complete energy as well into hydrogen via electrolysis, and then you can store energy, and then again you can convert hydrogen back to electricity if needed. So, that is like same thing that we discussed previously. So, these are the main component you need. So, you need like wind turbine, electrolyzer, hydrogen storage, fuel cell, or even like engine, which also can be utilized to produce electricity from hydrogen, and then different power electronics, inverter, converter that we mentioned, and then we need a microgrid controller as well. Like other application, it could be also having like similar application for remote community, like village, island, defense microgrid, industrial site. It could be for agriculture operation, like ports, mining, those sort of area. I mean, we can think of like hydrogen and wind powered microgrid. The challenges, some of them we already talked many times, like the cost, efficiency, hydrogen safety, and then I mean integrating multiple technology, the control optimization for real energy management system, and definitely like solar, we also have like wind variability as well. So, that's again could be either battery or the other option is the hydrogen, which we are talking about now. So, if you have got a hydrogen based microgrid, definitely I mean it would be long duration storage, not like the battery. Battery would be like a few hours, but here you would have like days, even like for month. So, that's like a I mean big advantages. It ideal for like remote islanded system, because if you go most of the cases islanded area, you will get like a good flow of wind, where you will get I mean enough wind speed. So, in that cases also I mean this microgrid would be a good solution for remote and islanded system. Like others, that also can be contributing to decarbonizing the country or area. Definitely for like other microgrid, it can be also improve energy security, continuity, and also like for sector coupling. So, hydrogen can be used for transport, heating, industry, not just for the electricity. So, the multiple sector can be connected together as well. So, again here I mean in the beginning I mean I will go quickly. So, wind power is like it's not like the fast application to produce electricity from wind. That people use wind for windmill for many decades back, to produce mechanical energy for other application. For example, let us say water pumping, sails to propel ships. So, we use I mean wind energy, but that was for other application. But recently the electricity from wind power is actually getting quite popular. So, as I mentioned, like the currently so the biggest capacity available in the market like 16 megawatt, and you see the rotor diameter is like 242 meters. Mainly it used for like an offshore wind farm, because that's quite very big, and it can generate up to like 80,000 megawatt hour of electricity annually, which can be utilized to power 20,000 homes. So, you see like only one single wind farm, how many homes actually can be supplied. So, that's one of the reason, as I said, like for 100% renewables or close to 100%, I mean solar is almost like impossible. So, we need wind and we need hydro and other option. So, now it's 16, you never know, like it might go like 20 or more than 20 in coming years. So, you might already have some knowledge about wind. So, you have like the blade, and then that you have got turbine, generator, control system. Also, normally from wind you find the output voltage like close to 700, 690, 700. So, you also need a transformer I mean when you're gonna connect with the main grid. Each of them have got their own function. So yeah, I mean again from wind, the blade or the turbine that gonna capture the energy converting from wind to mechanical, and once it rotates, definitely there is a gearbox, because you know that the speed of the wind is significantly lower than the speed of the generator, right. So, the generator speed much higher than the wind speed. So, we need like a gearbox in between, same thing like a transformer. So, the transformer for stepping up voltage from primary to secondary. So, this is also like the 2 speed. So, we need a gearbox as well. How we can model is very simple equation, that kinetic energy equation half mv square, right. From there you can easily develop whatever the power you are gonna get. So, this like that area that you are gonna capture for the wind for the turbine. So, if you consider that area A, where the air density rho, which is fixed, has got fixed value, so which has got that fixed value rho, then if you put it and converting like mass in terms of volume, then you're gonna get this equation. So, for any wind farm, you can use the same equation, and you can see like for considering the diameter, area, that wind speed, what sort of power you can get for a particular. So, it's just like giving one example, that 20 meter per second wind speed, blade rate 30 meter, what wind power you can get. But that's again like this is the input power, not like the output power. So, this is the input power, you're gonna get it just converting from this one to area, and then if you use the simple equation, you can see this sort of power you're gonna get. So, if you really want to design wind turbine, then this sort of modeling is needed, but for just doing simulation, I mean you don't need that. So, with diameter there is a like significant changes, whatever the output power you're gonna get, and that can be done from previous equation. And you can see that with the diameter, the relation is when you calculate the area, is relation is E square, right. So, with the radius, the relation is E square. What I am trying to say that if you just double the diameter, your power gonna be reduced by 4 times, because the relation is E square. And then whatever the input power is coming, to get the output power, actually you need to multiply this another coefficient, which is called like the power coefficient, and this power coefficient has got like a maximum value, because so far from the wind we can capture maximum 59% energy. You never would be go beyond that. Whatever the technology available, you cannot capture 100% energy from the available wind. So, this is like the theoretical value, 59.3%, but normally all the practical wind farm you can see, it would be around like 40%. So, let us say in the input, if you have got 100 kilowatt, you are gonna get maximum 40 kilowatt as a output in the wind farm. So, that thing also you need to consider when you are gonna design the microgrid and see what sort of power you are gonna get from the wind. So, it's not like the wind speed and then you use that equation, you say like this is the power I am getting. No, you have to consider the limitation from the output power that you are gonna get from the wind turbine. And also like with the wind speed, the relation is cube. Like if you see that equation is cube, right. So, if wind speed changes, the power output actually changes significantly. So, if it is wind speed get double, the power output will gonna be increased by 8 times, right. So, that is why the variation of the wind changes the output power significantly. Now, just this one just showing the simplification, that if you just get the idea, like for particular wind farm, what should be the diameter. I mean, that is given like very simple equation. So, for example, if you get like 10 megawatt wind farm, you need the diameter around 150, which is the one that used in Norway is like 144 meters. So, because here we are making some assumption just to simplify that equation, but what I am trying to say that based on the power, you can have a good idea about what will be the diameter. Now, when I talked about that wind power modeling, I talked about this 3, 4 speed. Now, what is that? Actually better would be, I mean, if you see here. So, initially if your speed is less than 3.54 meter per second, you will not get any output power from the wind farm, wind turbine. So, it has to be more than that value. So, once it goes like more than 3.54, which is called like cut in, then you are gonna get some output power, right. But when it is reaches like around 12, 14, you are gonna get rated output power from the wind farm. But it's not that if keep continue, you are gonna get more power, because it has got the rated. After rated, whatever speed, you are gonna get constant output power. But you know that for safety purpose, there is a speed, I mean, you cannot rotate more than that due to the mechanical safety and so on. So, what happened, like all the wind farm, they have got sensor and protection. So, when there is a wind gust like a tornado, they sense the wind and then they automatically shut down. So, that speed is like around 25. So, if you go more than that, then the wind turbine will be like automatically shut down. Now, how actually you can model the wind farm? That's I mean our interest when you are gonna model hydrogen wind farm with the other technology. Now, again these are the as I already mentioned that from wind, the wind turbine capture energy, mechanical is connected with the generator through the gearbox, and then we have got the generator which produces electrical power, and then depending on which technology used, because there are also many wind farm available in the market. Now, depending on that, it depending on like what sort of power electronics inverter converter we are using, then we have to model that one, and finally is going to be connecting with the electricity grid. So, when you are modeling, you have to model turbine, you have to model the gearbox, you have to model the generator, and then you have to model the inverter converter as well when you are doing the whole simulation. Okay. But for only planning purpose, you just do that simple power equation I mentioned. But for doing like non-linear simulation, you have to model each and every component of the whole energy conversion system. It is not only turbine, but the whole system that you need to model. So, this is one of the terminology you will see many cases when you study wind farm or wind technology, which is called actually TP speed ratio, but this is actually given the TP speed of the blade and the wind speed, and that ratio is actually given, and in many of the model they use with that terminology. So, better you also need that this is nothing but just the ratio between the the two speed. And then depending on the construction, it could be either horizontal, vertical, depending how it rotates. So, if you want to have like a small size wind turbine, then it would be like a vertical one. It could be having in your even like rooftop or in the community area, even it could be in the campus, because it's small, but it has got different types of like shape as well. Some of the shape even you will not understand this is a wind farm. It looks like a toy, so it's rotating, it looks quite fancy, but at the same time it produces electricity as well. But most of the commercial one, that gonna be like a horizontal, so it's rotate like horizontally, and it has got bigger capacity. This one most of the cases would be the kilowatt range, but this is like the megawatt range. Yeah, so now in terms of the generator, wind farm mainly use asynchronous. The normal machine, I mean normal generator we use in the power system, they use synchronous, but the wind farm normally use asynchronous, but there is the next generation wind farm, they are also planning to use synchronous generator, mainly permanent magnet synchronous generator. But here I mean mostly they use asynchronous, and asynchronous is that it could be either squirrel case or wound rotor types of machine. Again, I mean I'm not gonna go very detailed, probably might know, or if any of you don't know, if you want to model wind farm, you need to have some idea about both, I mean asynchronous as well as synchronous machine. And synchronous, again it could be like a permanent magnet, or it could be like a electromagnet as well. And each of them have got their advantages, disadvantages, but for wind farm, the next generation one, they are actually thinking of permanent magnet. So in terms of wind technology, there are like 4 technology types of technology available. So this is the first generation wind farm, which is called almost like a constant speed. Then we did have limited variable speed. Now this is the 3rd generation one. You will find most of the commercial microgrid, wind farm, wind technology, that's the variable speed with partial scale frequency converter, which is also called DFIG, doubly fed induction generator. And then the 4th one, which is more like R&D level, but that might be coming soon, and like in the commercial level as well. So that's like a full control. So the 3rd generation one, you have got partial control, but the 4th generation one, you will have like 100% control for both active and reactive power. And this one is showing the constant speed wind farm, wind turbine. And here you can say that this is quite similar, like the initially we have got turbine, gearbox, then the generator, which is squirrel cage induction generator. Now why actually we are using that capacitor? Because this is the additional component, this is not the part of the wind turbine. Because squirrel cage induction generator, it consumes reactive power from the system, so it has got like negative impact on the voltage. So that's why, I mean to control the voltage or to improve the power factor, we use the shunt capacitor. So this is quite compulsory. If you use this turbine, it has to be some additional compensating device with the turbine. And then we also use like a soft starter, and also this is that during the starting periods, this type of induction machine, they take high current from the system. So to limit that initial current, what we do, we like this switch is like open, so there is like additional resistor in series with the turbine. So that means this is limiting current coming from the grid. But once it is spin and rotate close to the rated speed, it produces the back EMF. That time current automatically reduce. So we don't need that additional resistance, because it's gonna be having some losses, because this is resistance. So that time it bypass. So this only use at the starting period, beginning. Good thing this is inexpensive. The technology is matured, but the problem is that we need additional compensating device to control the voltage. So, this is the next generation one. It is not like squirrel case. Squirrel case, as you know that the rotor is internally shorted, but for squirrel case the rotor is connected with the additional resistance box, which can be utilized to control the speed, but the control range is quite limited. That is why it is called limited, and this is resistance box. So, there will be like a power losses as well. So, again I mean that is why people are not interested for this type as well. So, this is the most popular one, and many of the modeling you will see that people in the literature they use this one doubly fatty induction generator, which is also called like partial power electronic converter. Why we call it partial? Because here like almost 70% power from the wind goes directly to the grid, not via power electronic converter. So, through this converter we have only 25 to 30% of the power actually transfer this path. So, why we do that? Because in that case, for example, if say your wind farm is wind turbine is 10 megawatt, then you need 10 multiply 0.3. So, inverter converter capacity will be only 3 megawatt, right? Because the inverter converter quite expensive, is very sensitive. If there is a disturbance, there is a possibility that it can damage. So, that is the reason we only use like 20 or 25% capacity, but still I mean you do not have control over 100%, but still you have control over 20 to 30%. So, still that good enough to control, provide both frequency and voltage control function. Again I mean for controlling purpose, I have just given like I mean for gearbox also, like there are different types of model available, third order, fifth order. So, many people use this first three equation to model that gearbox, and then like your generator, both rotor side, stator side, and then for this rotor side converter, grid side converter, also you need I mean different control here as well. So, in terms of control, what sort of control we need actually here? Mainly three types of control. One is for here for like the turbine, they use like the pitch control, and then for this rotor side converter we need one control, for grid side converter we need another control. So, once like you have that model, and then I mean depending on what sort of control and what other devices, then you can go for designing control. But this is the next generation one wind farm, where you can see that your both rotor I mean 100% power gonna be going to the grid through this converter inverter, but definitely you will have 100% control, but thing is that the inverter converter will be very, very expensive, because that or whatever capacity of the inverter converter, that has to match with the generator. So, if it is for example 10 megawatt, that also has to be 10 megawatt, which is at the end improve the performance, but it would be quite costly option. So, this is like one example of wind, hydrogen, you can say microgrid, or just like a could be with the grid connected as well. So, here you can see that we have got two wind turbine. So, as I mentioned like that, we need like a one piece controller to control like the piece depending on the like wind variation or wind direction. Sometimes we sense like the piece, just to make sure that you capture maximum energy available from the wind, and sometime also like if you have got very high wind, also I mean that helps I mean even to slightly bit for the protection purpose as well. and then you have got this you know um, both like generator side and the grid side. So, this is like the generator side controller, this is like the grid side controller. Now, this both controller has got different function. So, the one of the controller they mostly control the DC voltage, and another controller they control the active and reactive power, and then this output of the turbine is going to be connected with your electrolyzer through this again AC to DC and DC to DC converter. You could also have electrolyzer here, but we haven't done electrolyzer, but it could be done whatever like the hydrogen. You could have another electrolyzer and connect with the system as well. And then you have got like two types of load. One is resistive, another like a capacitive load. So, and then one you can actually do that modeling if you want, like working in this sort of configuration, and then you can do the simulation. Now, I already mentioned like that for pitch control, what actually we need with this, we need that speed input, the rotational speed, and then depending on the reference, it gonna be producing the pitch angle. But you know that the normally there is a like a maximum and minimum limit that we set. So, we set normally just to avoid the mechanical stress, we limited like plus minus 10. So, we control it, but it has to be like within limit. So, you put that limit maximum and minimum, and then the grid side generator side converter, which main purpose to maintain the DC voltage. So, here you see that the DC voltage input, from that it produces the reference current, and finally from that you gonna apply in your converter. But here what will happen that like that when there is a like a change like the power demand, for example, let us say when your power demand rise, what going to happen? For the DC voltage there is a balance between DC power and AC power. So, if one of them increases, so what will happening, you will find some changes, and based on that changes it gonna be producing the different reference that it's giving to the converter, and that will give you like to either to deliver more power to the grid, just to make sure that your DC voltage is constant. So, based on that either your load increase or load decrease, it gonna produce the control action just to make sure that constant. So, the other side, the grid side, as I said, this is more like reactive power, and speed, that's like also for real power as well. So, that's gonna be giving by your this control. Some of them also use like this MPPT concept here as well, depending on like whatever mechanical power we are getting, we can get like corresponding speed that gonna giving you like the maximum output power. And then you have got the grid side converter, which is again as I said like mostly controlling the voltage because it's connected with the grid. And then you also have the electrolyzer control. Again, this is like a very simple control just to maintain the voltage using the PI. And then here the simulation shows with different wind speed. So, initially this wind farm was, one of them was like a like off, and then only one of them was on, and with this input power was coming as a input to the electrolyzer, and then when that speed changes, how both of them behaving, and then at some stage the second one is also turned on, and when both of them have on, how they are behaving, and also like how the frequency also changing with respect to those wind changes in the system. So just to do like showing your stability, you can change the different parameters, and then you can see like how the system behaves. So as I say, like in Australia already we have like one then like in the operation in I think in Western Australia. So they already have hydrogen and solar and also some wind in the system. So like previously, I mean, I also given like some of the idea that probably you can think of if you want to work hydrogen and wind. Sometime it could be that both hydrogen, wind plus PV. So these are the some of the area people are still thinking to do more work, because they still need further work. So yeah, so these are the things probably I'll leave it to read at your, I mean, either now or later if you really want to work in that area. Thank you.
Efficiency in capturing wind power is 59.3%.
Yeah, that's the conversion. That's not the efficiency of the wind turbine.
Of capturing the wind power.
That's
That's
the maximum you can capture.
Yeah, that is an empirical value, or is it derived mathematically?
That is from that using that defined parameter that actually give the theoretical value. I mean, by modeling, through modeling, like, because in reality, I mean, like when actually it captured, so they found that, I mean, through even like they have also proved through experiment, actually they cannot go beyond that value. So that has been done theoretically, but also, I mean, practically, as I mentioned, like when you really deploy, you're gonna get maximum around 40%.
Thank you.